Hi AP Physics students. Today we are going to be talking about momentum, impulse, and collisions. The first equation we'll talk about is the equation for momentum, which is P. Pretty simple. P, momentum, equals mass times velocity, and our units are just kilograms times meters per second. Momentum is a vector because it has velocity. Take a moment to find this on your equation sheet. We can tie in forces and momentum together. As a reminder, this is Newton's second law, F equals ma. Now we can transform this so that it now includes momentum. Let's think about how we can do this. Momentum equals mass times velocity, and force equals mass times acceleration. So if I want to get acceleration equal to v, I would just have to do v over t. Mass times velocity is momentum over time. So therefore, this also gives us what the force is on the object. This also proves that I have to have a force to have momentum. The next equation we'll focus on is impulse. Impulse is force times time. Now let's derive our units for this. For force, remember it's kilogram meters per second square. I get that from F equals ma times seconds. Now I'm going to get kilogram meters per second, which are also the units for P. Very interesting. It's also a vector because it has force. So this is telling me that the change in momentum is equal to my impulse. Now here is how we can derive this. We saw earlier that force equals momentum over time. Now what I can do is I can solve for momentum, and I will get this equation, which is also equal to my impulse equation. Therefore, impulse is the change in momentum. Impulse is pretty straightforward. We talk about the change in momentum, and what I mean is that something is going one way with my velocity and then changes to a different velocity. Now, as it changes, there's some amount of time. And as we may expect, it is very small. And in this moment, this is where I have my change in my momentum, therefore, I have my impulse. Just like we have the conservation of energy, we also have the conservation of momentum. All the conservation of momentum is my initial total momentum is equal to my total final momentum. Now if I plug this in, this could look something like m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. Now that's definitely a lot to say, and it's easy to mess that up. This is kind of like our baseline equation when we are talking about collisions. There are different types of collisions, but it's important to distinguish my velocity before and after the collision. Let's define our different types of collisions. Our first type of collision that we have are inelastic collisions. This is a situation where I have two objects, and maybe one is moving, maybe they're both moving, and when they collide, they stick and move together. So at the end, they have a singular velocity. Now, if I look at my equation here, I have my initial velocity for both masses. And then since my velocity is the same, I can write my equation this way because they have singular velocities. Sometimes, or more like sometimes, often we'll find in these problems that one of the two objects are at rest to start. Now, something to think about that we'll answer later is my kinetic energy conserved? That is something that you should think about in each of these problems. I'm not going to answer it today, but it's something that we're going to look at later. My next type of collision is an elastic collision, which means when two objects collide, and once again, they can start moving towards each other, away from each other, one's at rest. Instead of sticking together, they bounce off. Now, one of the really big misconceptions about elastic collisions is that they're going to break apart in opposite directions. This is not necessarily true. When we start exploring a few different types of situations, you'll see that there are lots of different combinations that we could have. The equation stands the same here. The only thing that might change is if one thing's at rest, that would mean that one of my initial velocities would cancel out. Now finally, we have explosions. And explosions are when two things start at rest and then they move apart from each other, just like an explosion that we would think about in real life. Now in this situation, since both velocities are initially 0, that means this whole piece in front cancels out, which means my equation looks a little bit something like this. And this is the problem we're going to do next, so we can start looking at how the math works here. All right, so let's say that we have this situation, and we have this first car with a mass of m, and the second car with a mass of 2m. And this car is initially at rest, and my smaller car is moving at a velocity of 2v. Now they're going to collide and they're going to move together, which means I have an inelastic collision. So let's say I want to solve for my final velocity, which is typically what we're looking for in these problems. So if I have my initial mass and velocity, and I'm just going to write all this out. While things are going to cancel, it's important that I do. And then I have my masses together times my final velocity. It's important that I write this final velocity as VF, and you'll see why a little bit later. My 2m car starts at rest, which means I can cancel out this whole part right here because my velocity is equal to 0. Now I can plug in some numbers. So I have m, 2v equals, and my two masses together. It's easy to also forget this. And then I can simplify, make this a little bit nicer here. Okay, we'll see that masses cancel, which is kind of interesting, okay? But I still have a proportion, so I'll divide that by 3. So this means my final velocity of the system together is 2/3 v. So as we would expect, this would slow down based on the two masses. Now, while we notice that the variable for masses cancel, the proportion of numbers is still there. In class, we're going to explore a little bit more about how energy relates to this and look at a variety of different situations and see how much we can predict what's going on.